This is an AP Physics C video reviewing average speed, average velocity, and average acceleration. Remember that average speed is the distance divided by time. So distance, remember, is a scalar, so the direction doesn't matter. Whereas average velocity is the displacement over time, and displacement is a vector, therefore average velocity is a vector. Just like, since distance is a scalar, average speed is a scalar, meaning for average speed, direction doesn't matter. But for the vectors, direction does matter. Direction does matter. So those are our definitions of average speed and average velocity. Now, remember that there's no sign for average speed because it's a scalar, and for average velocity, the sign gives us the direction. Average acceleration tells us how fast the velocity is changing with respect to time. So it's the change in velocity over the change in time. And once again, the sign tells us the direction. Positive, by convention, is to the right or upward. Left is negative, and so is downward. In this sample problem, it says a motorist drives north at 20 meters per second for 20 kilometers and then continues north at 30 meters per second for another 20 kilometers. What is his average velocity? So let's say this direction is north, and let's use motion maps to help solve this problem. So 20 meters per second for 20 kilometers. So let's label this as being 20 kilometers. And then it says another 20 kilometers, but this time at 30 meters per second. And we want to find the average velocity. So our average velocity is equal to the displacement divided by the time. So we know the displacement is 20 kilometers plus 20 kilometers, which is 40,000 meters. And so we need to find the time. So we should use basically our velocity is equal to displacement divided by time for each of these sections. So for that first section, we're going 20 meters per second. And we're going 20,000 meters over time t1. If we solve that for t1, we find that that takes 1,000 seconds. And then for a part where we're going 30 meters per second and still going 20,000 meters, solving that for t2, for the other time, gives us about 667 seconds. So this is our total time here, which we'll have to add the 1,000 to the 667 seconds. So 1,667 seconds. And that gives us an average velocity of 24 meters per second. So the key here is realizing that you have to have the entire displacement and use the entire time. And because we said north is positive, we need to make sure we emphasize that, or just simply say north. It's okay to be redundant. Now for this next question, it says it takes a motorist 1 minute to change the speed from 20 meters per second to 30 meters per second. So 20 meters per second in the positive direction, and then speeding up to get to 30 meters per second. and that takes 1 minute or 60 seconds. And we know that the average acceleration is calculated by taking the change in velocity over time. These are the two endpoints, v final minus v initial, divided by the change in time. So 30 meters per second minus 20 meters per second divided by 60 seconds gives us approximately 0.17 meters per second squared. Meters per second squared, remember, is the units for acceleration. Now, let's look at how we would calculate average velocity from a graph. So remember, our equation is the change in position over the change in time. So let's look at A and B, those two positions, and how we would find the average velocity. So to find the slope, we need to take the rise, which is the displacement, divided by the run. And that's how we would go about solving for that average velocity. Now, if it's a curved graph, still we're going to look at the two endpoints at location B and location X. I'm sorry, location B and location A. And we would draw a line from those two endpoints. And our equation for the velocity would still be based on those two endpoints, the rise divided by the run. Now the average acceleration is very similar. Take the rise over the run when it's a linear graph. And even if it's not a linear graph, we would do the same thing. We would take the two endpoints. So it might be difficult to see this, but there's a line, or there's a curve that goes like that, and it says from the graph determine the average velocity for the particle when it moves from point A to point B. Okay, so remember, this is average velocity requires that we solve for the displacement over time. So average velocity is the displacement, which is delta x over delta t. So that would be at the location of B, the position of B minus the position at A. Remember, it's always final minus initial. So TB minus TA. Again, only the two endpoints matter. So the final endpoint is at minus 1 meter. And we start at 0 meters. As far as the time's concerned, that took 0.5 seconds. And we start at 0 seconds, and that gets us an answer approximately, it actually gets us the answer of -2 meters per second. Okay? All right, so that's how we go about finding the average velocity on a graph. To find the average speed, remember, that's the distance divided by the time. So when we're going from here to here, that's about 2 meters. So remember, our average speed, is the distance divided by the time. So the distance, if we look at our total distance from here to here, we go 2 meters. And then from here to there, we go another 2 meters. And then from there to there, we go, looks like another 1 meter. Okay. Now we're calculating out here the total distance, not the displacement. And that's taking 0.5 seconds. So instead we would have 5 meters divided by 0.5 seconds, and we get 10 meters per second. So notice that is a completely different value than for the average velocity because of our definition of the average speed. The average speed is a distance over the time, whereas if we go and look back, our average velocity was the displacement over the time. In other words, we're only concerned about the two endpoints. So that's the difference between that average speed and average velocity. Now let's look at instantaneous speed, velocity, and acceleration quickly here. So the average velocity, like we said from a graph, is that between time A and time B, we have to look at the slope. So that's how we go about finding the average velocity. We take the slope from those 2 points. Now, if we start to move A closer to B, notice what happens. There gets to a point where A and B are effectively at the same point, and the time difference is effectively 0. Now, that connecting line is what we call a tangent line to the curve. Okay, so the velocity at that instant of time is represented by the slope of the tangent line. So this tangent line slope would be what we call the instantaneous velocity. Okay, so that's velocity at that particular instant. So if we wanted to find the instantaneous velocity on this graph at location B, we would have to first find the slope of the tangent line. So we'd have to, so let's go back and draw this line back in there. So at this point, we need to draw our tangent line at location B. Okay, we kind of have to eyeball that. And then we calculate out the slope. The rise is -6 meters and the run is about 0.28 seconds. So to calculate the velocity, we take the rise, -6, divided by the run of 0.28, and we get -21.4 meters per second. So again, instantaneous speed and instantaneous velocity is by finding the slope of the tangent line. Only difference is for instantaneous velocity, that would take into account direction, whereas for instantaneous speed, direction wouldn't matter. So let's look at average and instantaneous acceleration. It's really similar as well. So if I looked at the average acceleration from A to B, I would have to take 2 connecting points and find the slope of that line. But if I wanted to find the instantaneous velocity the instantaneous acceleration, this is instantaneous acceleration, it would once again be the slope of the tangent at that curve to be the instantaneous acceleration. A few other things. So reminders that the acceleration is negative when the curve is concave down. This is review. And instantaneous acceleration, or acceleration in general, is positive when the curve is concave up. And instantaneous acceleration is 0 where the slope is constant.